Hello students. Today's topic is large-scale cultures. It includes scale-up in both suspension and monolayer cultures. Based on the application of cell line culture, they can be categorized into three groups. First, products from cells. Example, antibodies, vaccines, hormones. Second, cells as products. Example for cell therapy and transplantation. And third, cells used for testing pharmaceutical products and chemicals, etc. Some of the permanent cell lines used in pharma industry are Chinese hamster ovary cells, CHO, baby hamster cells, human embryonic kidney cells, HEK293 to name some. The table here enlists the properties of some of the permanent cell lines. Large-scale production of pharmaceutical products are done in bioreactors. It is done in a controlled condition. The use of naturally or recombinant cells, organs, tissues for products of industrial or pharmaceutical use is termed as bioprocess. The animal cell bioreactor should be simple in design and should be able to hold large number of organisms per unit volume with uniform distribution. There should be a controlled supply of carbon dioxide rich air and a well controlled environment. The reactor should be agitated and aerated gently. There should be provisions for removal of toxic substances like lactic acid and ammonia that are synthesized during the metabolism of the cells. The mammalian cells used in bioprocess could be primary cell line, cell strains, permanent cell lines, and hybridoma cells. Certain features to be kept in mind while designing animal cell bioreactors are animal cells are fragile and larger in size. Growth rate is slower when compared to bacterial and fungal growth. Animal cell lines also release certain toxic substances like ammonia and lactate during growth. Hence, it should be monitored and removed. Based on cell line character, scale-up processes of mammalian cells can be divided into two categories, scale-up in suspension and scale-up in monolayer cultures. I would start with the monolayer cultures first. One of the methods to scale up monolayer is Nuc cell factory. It is composed of stacked rectangular petri dishes with large surface area, interconnected at two adjacent corners as shown in the figure. It is provided with ports which facilitate venting, filling medium, and harvesting of cells. The number of trays are decided based on the requirement. Monolayers are grown in these trays and then incubated. The main disadvantage of nut factory is that cell growth cannot be monitored as the petri dishes are stacked. Multi-array disc, spiral and tube cultures. In this type, the surface area of growth of monolayers culture is increased by using spirals, discs or tubes as shown in the figure. Next, roller bottle culture. In this type of culture, the surface area is increased by seeding the cells on the curved surface area of a large bottle or tube that can be rolled around its axis. The bottles are then attached to carbon dioxide incubators and rolled to expose the cell monolayer to the medium, as shown in the figure. The advantage of roller bottle culture is that it provides an increased surface area for monolayer culture and hence increase the production of metabolites from the cell. Microcarrier beads. In this type of culture, the cells are seeded on the bead surfaces and then grown in flask. This increases the surface area for monolayer culture. The density and size, that is diameter of the beads, can be standardized based on the requirement. Perfused monolayer culture. In this, the growth surface area of monolayer cultures are perfused to facilitate medium replacement and product formation and recovery. Perfusion can be carried out with pumps, oxygenators, and other control systems. The figure below shows a schematic representation of a bioreactor, perfused bioreactor that can be used both for suspension and immobilized cultures. The various types of perfused monolayer cultures are fluid bed reactors, membrane perfusions, hollow fiber perfusion, matrix perfusion, and microencapsulation. Fixed bed reactors. In this type of culture, the cells are grown on microbeads and these microbeads are packed into the bioreactor. These beads are porous in nature. The nutrient medium is perfused upward through the bed. The bioreactor maintains controlled conditions. Advantage of this method is easy collection of end product and spent media. The diagram below shows the fixed bed bioreactor and a diagrammatic representation of the beads. Fluidized bed bioreactors. In this type of reactor, cell monolayers are grown on outer or inner surface of beads. The beads are then suspended in a stream of medium. The flow rate of the medium should be maintained and should be equal to the sedimentation rate of the beads so that they remain dispersed in the nutrient medium. Membrane perfusion bioreactors. In this type of culture system, the monolayer of cell is compartmentalized by means of permeable filters or sheets. Example, in the figure given below, the cells are compartmentalized within a membrane with a molecular cutoff. The membrane is permeable to gas and nutrients. The nutrient compartment is placed above the cell component. Hollow fiber perfusion culture. In this type of bioreactors, cells are grown on hollow fibers. The hollow fibers are arranged into cylindrical cartridges with ports on both ends for outlet and inlet of media and nutrients. Based on to which surface the cells are grown, they are categorized into two types: internal perfusion series and external perfusion series. In internal perfusion series, the cells are grown outside the surface of the hollow fiber, that is extraluminal. The nutrient media flows inside the hollow fiber while the gases outside the fiber. This structure is easy for removal of particles which may get clogged in the hollow fiber and can be removed by liquid back flushing. In the external perfusion series, the cells are grown inside the fiber, that is intraluminal. The nutrient media flows outside the hollow fiber while the dissolved gases go into the hollow fiber. The matrix perfusion culture. This type of bioreactor is designed in such a way that there is a continuous supply of nutrients and the spent and harvest media can be collected without disturbing the monolayer. It is designed in such a way that it consists of four vessels: the matrix vessel, the mixing vessel, harvest tank, and feed tank, as shown in the figure below. The matrix vessel is packed with microbeads containing the monolayer culture. The mixing vessel ensures mixing of the nutrient media. The harvest tank allows harvesting of the culture media, and the feed tank acts as an external culture media reservoir. Microencapsulation. In this technique, the cells are entrapped or encapsulated in sodium alginate. These encapsulated cells are then used in bioreactors. The gel forms a covering over the cell. The nutrients and gases in the medium can penetrate through the gel. However, the gel acts as a barrier for high molecular weight molecules or products. Thus, they remain entrapped in the vesicles. The products can then be recovered by reducing the concentration of divalent cations. The figure here shows the example of a process of encapsulation of insect cells under sterile conditions. These gels have low immunoreactivity and can be implanted in vivo. Scale up in suspension cultures. In case of bioreactors used in animal cell culture, the agitation rate should be less, not over 120 to 150 rpm, as the cells are fragile. In column and airlift bioreactors, operating at high aeration rates may also cause shear damage to cells. These criteria should be looked while designing a suspension culture bioreactor for animal cells. Stirred tank bioreactors. It is the most conventional bioreactor and it's a batch culture. The size of the stirred tank reactor varies from 2 liters to 20,000 liters. The figure here represents a simple model of a stirred tank bioreactor. The stirring speed is low and generally done by using magnetic bars for small volume cultures. For larger volume cultures, magnetized rotating pendulum is used in some cases. Provisions or ports are provided for supply of nutrients, gases like carbon dioxide and air, and addition of cells. Probes are used to check and maintain pH, temperature, foaming, etc. For large-scale cultures, the culture is started from a small flask culture. STRs has been successfully used for production of vaccines and monoclonal antibodies. To sustain a high cell viability and cell division, the media needs to be replenished intermediately and the metabolites need to be removed. This is achieved by continuous flow culture. A simple design of a continuous flow culture is given below. Under perfusion control, the products can be constantly harvested. The constant addition of nutrients and removal of toxins from the culture leads to rapid division of cells, thereby increasing cell density, and also maintain a steady production of the metabolite. Bubble-driven bioreactors. The bubble column bioreactors are generally cylindrical in shape with perforated pipes or plates as sparges. Air or gas is introduced from the base of the bioreactor. A disadvantage of this bioreactor is that proper mixing of nutrient media does not occur. Airlift bioreactor. Airlift bioreactor differs from the bubble bioreactor as it has a draft tube inside. The air or gas is pumped in from the bottom and released at the top. The region from which the bubbles are sparged is called as the air riser. It may be from inside or outside the draft tube. Counter to this, liquid flows in downward direction in down corner. This results in proper mixing of media, reduces bubble collisions, and equalizes the shear forces. In airlift bioreactors, there is a zone known as the disengagement zone. The bioreactor is designed in such a way that the top of the bioreactor has a sudden widening. This leads to reduction in bubble velocity and prevents loss of media due to aerosol formation. With this, I wind up the present topic, Scale Up by Monolayer and Suspension Culture. Thank you.